Welcome to the next lecture on properties of pure substance. So, what are the different properties of pure substance? A pure substance is defined as a material that has a uniform or a fixed chemical composition throughout its volume and does not change during thermodynamic process regardless of phase change. This type of pure substances in thermodynamics is fundamental because it allows for a consistent and a predictable analysis of energy exchange. So, the key thermodynamic properties are going to be pressure, temperature, specific volume, specific internal energy U, enthalpy and entropy. So, pressure, temperature, specific volume, specific internal energy, specific enthalpy and specific entropy. These properties are related and their values significantly depend on the form whatever they exist. They can exist in one form or they can coexist in two forms. The pure substance exhibits predictable behavior that can be mapped and understood through thermodynamic diagram and equations of state. So, during heating, cooling and the phase transition, the relationship among these properties help engineers design and optimize systems for turbines, compression, boiler and condensation. So, with this now you will be able to easily appreciate, I know this diagram for a pure substance. So, now I have the processes like boiling, cooling, condensation, expansion, compression, whatever it is I know. When I wanted to compress, I increase the pressure. So, I try to maintain temperature, I try to maintain pressure, I only try to reduce the volume. So, whatever it is, or I try to reduce the volume and I allow the temperature to go whatever it is. So, that is also possible. Suppose you want two things to be isolated, then you have to plan your engineering system so nicely. So, that is what it is. So, the engineering processes are known, pure material responses are known. Now, I try to map so that I can get the best use of it such that my energy efficiencies are high. So, here you also saw liquid, vapor, supercritical fluids, all these things you saw, right. So, when you stay all these supercritical fluids, what happens to the basic thermodynamic property? That is what is the next question. So, then it is a good idea to find out for a working fluid, what is the temperature or what is the property, what is the values of the property, it is very important to do. So, we try to use this triple point diagram, we try to use the surface and then we try to extract the data. State the pure substance include pressure, temperature, specific volume, specific internal energy, specific enthalpy and specific entropy. By knowing any two independent intensive property and the state of the pure substance, you can typically determine the remaining properties can be calculated using the thermodynamic table and appropriate models. So, this is very important. By knowing any two independent intensive property PV, PT, TV, if you do it. So, then what happens? You two properties, then the state of a pure substance can typically be determined and the remaining properties can be calculated using the thermodynamic table or appropriate model. This makes the concept of pure substance and their properties an essential foundation for real world application and thermal energy problems. Volume, enthalpy and internal energy. Among the various thermodynamic properties of a pure substance, specific volume, specific internal energy and specific enthalpy plays a very important role. What is specific volume? Specific volume is defined as a volume occupied per unit mass of a substance, that is meter cube by kg. So, is defined as a volume occupied per unit mass of a substance as an indicator of the spatial configuration of the molecules and helps determine the fluid density. It is especially crucial in analyzing expansion and compression process, where volume changes are central to performance. So, specific volume is a volume occupied per unit mass of substance. Specific internal energy, it is a measure of microscopic energy contained within the molecule of a substance stemming from molecular motion and interaction at atomic level. It excludes any kinetic or potential energy due to the movement of a substance as a whole and is particularly significant in closed system energy balance. So, you can see here kinetic energy is the black line which is drawing, arrows which are drawing are kinetic energy, the red ones which is connecting the molecules are potential energy. So, specific internal energy is a measure of the microscopic energy contained within the molecule of the substance, stemming from molecular motion and interaction at atomic level. Enthalpy, enthalpy is defined as H is equal to U plus PV, where it is nothing but a combined internal energy with the flow work PV needed to displace the surrounding environment during a constant pressure process. Is a derived property. This is very important. Is a derived property defined as enthalpy is nothing but H is equal to U plus PV, where combining U is the internal energy and the PV is the with the flow work. Enthalpy is extensively used in open system. Enthalpy is extensively used in open system control volume, such as nozzles, diffusers and heat exchangers, where mass enters and exits the system continuously. Like for a nozzle is this, mass enters and exits continuously. Enthalpy is extensively used in open system such as nozzles, diffusers and heat exchangers, where mass enters and exits that system continuously. So, this is the pictorial diagram of the enthalpy. H is equal to U plus PV. So, volume, enthalpy and internal energy, they are three properties that are typically tabulated for substance like water and refrigerant at various pressures and temperature, enabling engineers to perform accurate energy calculations across a wide range of applications for power plant engineering and refrigeration and air conditioning systems. So, you have to know at what pressure, what temperature this gets converted. So, that can be extracted from a table. So, there is a, so from a pictorial there is a model also. Today you have programs, software codes written. So, you can put the temperature and see what happens to the pressure, or you can have a pictorial representation and wherein which you have a pointer which drags the point at various portions and you can try to see what is the response of these phases. So, there are a lot of advanced tools which are coming here. Why? Because once you know this, then you can plan your engineering system. Saturation temperature and saturated pressure. The saturated temperature and saturated pressure are critical thermodynamic properties that define the precise condition under which a pure substance undergoes a phase change from liquid and vapor. There is a transition for a given pressure. The saturation temperature is a temperature at which the substance begins to boil or condense for a given temperature. At this point, it can get converted into solid to liquid or liquid back to solid, right. So, during heating and during cooling, so beginning of boiling or condensation can be done. So, if you go by the TS diagram, so this is where the condensation starts, right. Boiling start, boiling end. The saturation pressure is the corresponding pressure at which the phase change occurs from liquid to gas or solid to liquid. So, saturation pressure. So, these 2 points are very important, saturation temperature and saturation pressure. These properties are uniquely related for each substance and often plotted in a PT diagram, forming a saturation curve that culminates at the critical point. Below the critical point, the substance can exist in distinct liquid and vapor phase, and the phase change process occurs at a constant temperature or pressure. For example, at standard atmospheric pressure 1 atmosphere, water has a saturation temperature of 100 degrees Celsius. After that or above that, it starts boiling. If the pressure is increased, as in the pressure cooker, the saturation temperature also rises. That allows the food to cook faster. P is directly proportional to T, where volume is constant. Conversely, under vacuum condition, the water can boil. You put water inside a container and you reduce the pressure. The water can boil at a much lower temperature. Now, friends, what is the lead statement you get? So, if you want to change the phase, you can increase the temperature or you can increase the pressure. When you increase the pressure at a lower temperature, the water starts boiling. So, now you have to plan your process and make it energy efficient. If you want only a phase change, how do I get it done? That is what it is. These saturation properties are fundamental to design and analysis of a system like steam generator, condenser and refrigeration units. Friends, I am repeatedly telling you that there are only 3 parameters: pressure, volume, temperature. There are 3 phases: solid, liquid, gas. So, now is there a distinct point where it goes solid to liquid, liquid to gas? Is there a distinct point? Yes, there is a distinct point. If that has to happen, what is the pressure, volume, temperature behavior? If you want to have a smooth sail transition, then what do you do? How do you do? For each of these transition, there is a process: expansion, condensation, compression, right? You have boiling, you have so many processes. So, that has to be linked and understood. And can I get it done for any given material? It is difficult. So, what we do is we try to do it for a pure material. In a pure material, what they would have done is they have established tables, and that tables they try to say very clearly at this pressure, this temperature, what will be the vapor pressure or what will be the vapor content. They will try to give it in a plot, like what we saw in a triple plot or we saw a 3D model. From there, they will try to saturate. So, this is what is important. Quality, dryness fraction is another important parameter which is a quality. In thermodynamics, quality, also known as dryness fraction, is a crucial parameter used to describe the state of saturated mixture of pure substance, specifically during liquid vapor phase change. When does a liquid vapor phase change? This is saturated liquid, this is saturated vapor, this point, right. So, the quality or the dryness fraction is defined as a ratio of the mass of vapor to the total mass of the mixture and is denoted by a symbol X. This property is significant. Why? Because in the saturated region, the substance does not exist entirely as liquid or vapor, but it exists in two-phase mixture, and the quality quantifies how much of it has turned into vapor at this point. Critical point, it changes, right? Close to this region you can keep. And in real time, you will never have a clear distinct point, is very difficult. You will have a small range. So, this is very important. Quality or dryness fraction is defined as a ratio of the mass of vapor to the mass of the mixture. So, the dryness fraction X is mathematically defined as X is equal to m vapor divided by m liquid plus m vapor, which is m vapor divided by total, where X is the quality or dryness fraction, which can range between 0 to 1. So, m is the mass of a vapor, m is the mass of liquid phase, this is vapor phase. Total mixture is given here. X equal to 0 implies 100% saturated liquid, no vapor at all. X equal to 1, it can range between 0 to 1. If X is 1, it is completely vapor, no liquid at all. If it is between X and 1, lies the saturation mixture, a wet region. So, that is plotted from this graph. When X equal to 0, when X equal to 1, Now you see how, what is that, we have plotted it for various this thing. So here it is T and TS diagram. So you will try to see, this is a hump we have, this is liquid plus vapor, this is vapor. So now you will try to see what happens when x equal to 0.25, x equal to 0.5, when x equal to 0.75. So when that meets a constant temperature line, so what is the response and then what is the entropy you get. So this is the dryness fraction which is defined. A point A, B and C at various pressures indicate the situation where the mass of the vapor reaches 25%, 50% and 75%. When you go down, you can see here 25%, 50% and 75%, A, B and C. At point A, the mass of the liquid is 75%. At A, mass of the liquid is 75%, this one, this line, 75%, and the mass of the vapor is 25% of the total mass. At point B, it is 50% liquid and 50% of the is the vapor mass. 75% is vapor and 25% is liquid mass. The line passes through a point A, B and C at a constant quality line of 0.25, 0.5 and 0.75 respectively. The constant quality line starts from the critical point. The critical point only we saw where there is a transition. So, in a saturated mixture region, properties such as specific volume, internal energy, enthalpy, entropy vary with the quality, dryness fraction, right, and can be calculated as Y equal to YF is a property of the saturated liquid X times the YFG. So, where Y is the desired property of the mixture which is given in volume, specific energy, enthalpy and entropy is a desired property given. So, YF is the property of the saturated liquid, YF is a liquid, and YG is the vapor. This is liquid, this is vapor, and X is a mixture of Y and F. So, YGF, this is nothing but YFG is nothing but YG minus YF. YF is property of saturated liquid, YG is property of saturated of vapor. So, you subtract and you get YG. So, the difference between saturated vapor and the saturation liquid point is YFG, is X times. So, the specific volume of a mixture V is represented as VF into this. So, this can be VG minus VF. So, specific internal energy mixture U is equal to this, H is equal to this and S is equal to this. Let us take one condition. So, VF is nothing but is the volume of the property of the saturated liquid, and then this is the difference. So, you are trying to represent it in this way. These relationships are particularly useful because most thermodynamic tables, steam table, lists only the saturated liquid and saturated vapor values at a given pressure and temperature. So, with known quality X, any intermediate points can be calculated. That is what we are saying. So, the concept of quality is foundational in analyzing thermodynamic system such as steam turbine, condenser, boiler or refrigeration unit. For instance, in a steam turbine, the inlet steam should ideally be dry or superheated to avoid blade erosion caused by liquid droplet. Because it is completely vapor, it is going to be easy, because the vapor hitting on the turbine blade, it will start rotating. If there is a molecule of water along with the vapor at very high pressures, then what happens? This becomes like a small bullet which is trying to hit on the blade. The blades are having a profile. So, it is very difficult to manufacture blades. So, they always will try to have a dry or a superheated steam to get inside. Engineers often calculate the dryness fraction at various points to determine the thermal efficiency and the entropy generation. Additionally, in energy balance calculation also for we will see Rankine cycle and refrigeration cycle, we knowing the quality helps us to find out what is the heat transfer and what is the work done. So, for energy balance, heat transfer, work done, everywhere this PV diagram, TS diagram, the dryness comes into existence. And dryness, you know that it is 25%, 50%, 75%, you can try to define. So, finally, we will try to see what is a supercritical fluid behavior. In the thermodynamics, the critical point of a pure substance represents a unique condition at which distinction between liquid and vapor phase ceases to exist, between liquid and vapor phase. This point is characterized by specific critical temperature Tc, and the pressure at this point is called as Pc, and the volume is called as Vc, beyond which the substance enters into a supercritical state. At this state, the fluid exhibits property of both gas and liquid, as it is referred as supercritical fluid. Here the property can exist both in gas and liquid form. These fluids do not undergo phase change in the traditional sense. Instead, their density and other properties vary continuously with pressure and temperature, allowing them to behave like a highly compressed liquid or a dense gas depending on the condition. So, this is very important, supercritical fluid. So, supercritical fluid exhibits both the property of a gas and a liquid. So, what is that? Allowing them to behave like a highly compressed fluid. When you use a highly compressed fluid, energy transition is very high. So, the work done will be very high. So, or the dense gas depending on the condition. A supercritical fluid exists at a condition above the critical temperature. T is greater than Tc and P is greater than Pc. The SCF are unique in that they have liquid-like density, allowing for high solventing power, exhibits gas-like viscosity, enabling rapid diffusion entering inside, have tunable property, small change in temperature or phase leading to significant change in density or other physical property, have liquid-like density, allowing for high solvating power. It exhibits like a gas, rapid diffusion. Tunable property, a small change in temperature or pressure leading to significant change in density and other properties. Density is mass by volume. Now, you should understand when it is moved, how does it happen. These features make SCF extremely valuable in engineering applications such as supercritical extraction, clean energy systems, supercritical water oxidation and supercritical Rankine cycle for efficient power generation. So, the critical point is defined as the highest temperature and pressure at which the substance can coexist in equilibrium in liquid and vapor phase. So, mathematically T equal to Ts, P equal to Ps. So, the saturated liquid and the saturated vapor state becomes identical. So, it can be represented in this ways: fluid is equal to gas. Beyond this point, no latent heat vaporization exists because there is no distinct phase change happening at this point. So, they are now called a cutting edge technology. Supercritical CO2 extraction is very much talked about for decaffeinating coffee, extracting essential oil and pharmaceutical purification. All these places we use supercritical CO2 extractions are done. Supercritical water reactors are the next generation nuclear power plant using Rankine cycle. It improves the efficiency in a power plant by operating a critical fluid. Working fluid can be water or CO2, enhancing oil recovery, EOR. A seed is there, from the seed you want to extract oil. When we use a supercritical CO2 injected into the oil well, you can try to extract more EOR. This unique ability to combine solvency, diffusivity and compressibility makes them an ideal fluid for clean and efficient energy and separation process. Friends, in this lecture, we saw what are pure substance, what are the different phases of pure substance, what do you understand by P, V, T diagrams, then a combination of this, then a three-dimensional plot of it, Then why is the study of properties of pure substances is very important, thermodynamics. Then basic properties like volume, enthalpy, internal energy and entropy we saw. Then what are saturated pressure, what are saturated temperature, what is the quality which is described, the quality of air or the quality or dryness fraction of air was dealt. And finally, we saw supercritical fluids, why are they very important as of today and where are they going to be used. So, these are some of the topics we discussed in this lecture. This lecture is going to be the fundamentals for your cycles what we study in the future. So, before I close, some examples I wanted to give you so that you can try to do those experiments or fundamental studies for your own understanding. One is the supercritical fluid they are talking about. So, now it is very clear if you operate in supercritical fluid, it is going to give us a higher yield. But what puts the limitation? I just wanted you to browse through. If it is so easy, why are we not able to do? That is point number one. Second thing is, we have been talking about turbine. This turbine is nothing but it is a disc. On the disc, there will be lot of blades. What are these blade profiles? 2. 3. Typically, try to look at the cross section of the fan which rotates above you. Take a blade and try to take at several sections what is its profile. That is the third thing. Fourth thing, when there is a relative humidity very high in the atmosphere, what do you feel when you run the fan at high speeds? And on a dry sunny day, when you try to run the fan at very high speeds, what is the response or what do you feel? Then when you switch on the AC, and then you parallelly switch on the fan, when do you enjoy the coolness in the room? What is the time period? The next time you do not switch off the fan, run the AC for maybe half an hour and then you switch on the fan. What do you feel? The third thing is, you run the AC for 1 hour, then switch on the fan, switch off the AC, when does the coolness reduce? These are some of the real time experiments which you can do by yourself, right? And then start understanding how is engineering playing an important role, keeping this pressure, volume, temperature, humidity. Relative humidity is nothing but air present in water. When you go to a very high temperature, it is steam present in water, in air. So, you can understand the implications of it. So, if you do these experiments, you will start enjoying this course. These are some of the standard references which we have been using for this lecture, and thank you so much for being with me in this course till now. Thank you.